Here we're going to be doing problems going backwards, hydrolyzing acetals to the original carbonyl compound. I have found that there is somewhat of a struggle of students trying to do problems, particularly when it's about opening a cyclic acetal. So first, acetal are stable under basic conditions. So this is one reason why we, for example, protect carbonyl groups using ethylene glycol. Under acidic conditions, we form a cyclic acetal. And since that's stable under acidic conditions, if we have other functional group or things that we need to do in the molecule, that will stay as is so long that my work is done under basic conditions. But this reaction is reversible, and that can be hydrolyzed back. So let's see how this is happening. And for that, we're gonna, well, first, let's do one example of this molecule, which is simpler in than one cyclic compound. So in acidic condition, the first step that we're gonna be proposing is protonation of one of the R groups and going backwards. So that's hydronium, and I'm going to be doing this. So now that I have that, I'm going to go and put it here so that I have more room. So now I have OR, and that R, remember, well, it says R prime because I said RR. So let's be consistent with that. Okay, so this was R prime, and here I had OH and R prime, so that's formal positive charge. So next step, what we're going to be doing is reforming a carbonyl group. So we're going to be doing that. And now this is a good leading group. So next, I'm having then this, and now I have here R prime. And of course, I know that's formal positive charge. Plus, I had already one molecule of alcohol that had departed. So next step in doing the hydrolysis, actually, the hydrolysis, remember, is a reaction with water. So we're going to be doing a nucleophilic attack by water. And when you see this species here has a formal positive charge. So you can do a resonance structure here, and you notice that if I do so, I'm going to have OR in here positive. So in other words, that formal positive here, what it does is makes this carbon more electrophilic. And so we will have the nucleophilic attack by water. So here it is, and I'm moving those electrons over. So when I do my nucleophilic attack, I'm going to have R, and now I'm writing my water on this side. I had attack with this, so now this is formal positive, and this is OR. Now to remove the other molecule of alcohol, I need to proton transfer steps, in which I'm going to be removing one H here and putting one H on the other end. So I'm going to do two little arrows to illustrate that I need to remove that. And that is done, for example, water gets this. Removing that, but then I need to protonate over the other oxygen. And this is similar to what we did here. And so in doing so, two proton transfer steps, I'm going to now have this. And now OH. And this structure, by the way, is like protonated amine-acetal. And the amine-acetal is an intermediate in both directions, both in the acetal formation or the hydrolysis. This is a hydrolysis of an acetal. So in next step you will do is this, if you're asked for a mechanism, of course. And so that's our prime. And now you have formed this, is you're almost there, because all you have here is now OH plus. So an extra H. And what we're doing here is simply another proton transfer step to remove that H. And we're here. So that is a hydrolysis of the acetal under acidic conditions. Again, stable under does a cyclic acetal to protect aldehydes and ketones, but acetals in general, these are stable molecules under basic conditions, but we can hydrolyze it back. So now, let's work in the following video. I'm going to be doing hydrolysis of acetals, but this time I'm going to be using cyclic acetals. And also, I have cyclic N-amines and imines. So we're going to be hydrolyzing those. Any of those could be hydrolyzed back to the carbonyl compound under acidic conditions.